We are going to discuss about problems based on butterworth and chebyshev filter along with that bilinear transformation. In the last video we discussed about characteristics of chebyshev filter and butterworth filter. Today we are trying to discuss about problems based on butterworth filter and chebyshev filter. Along with that we are going to discuss about problems based on bilinear transformation. So we know that what is bilinear transformation technique means. If I have two bilinear transformation, the numerator and denominator, we can call it as a bilinear transform. So we can design a digital filter by using analog filter. This is one of the transformation technique in order to design analog digital filter. So that is bilinear transformation. Let's see how to solve the problems based on this. So this is a problem statement they are given, that is the system function of the analog filter is given as HA of S. This is the transfer function which is equal to S plus 0.1 divided by S plus 0.1 whole square plus 16. So obtain the system function of the digital filter using a bilinear transformation technique. BLT is nothing but bilinear transformation technique, which is resonant at omega r, which is equal to pi by 2. So let's see the solution. So first what we need to do, we need to identify what are all the poles we have in this case. So the poles means the denominator term always represent a poles. So poles at we have, if I equate it to 0, we'll get a 2 poles here. One is at S plus 0.1 minus J4, another one is at S plus 0.1 plus J4. So finally we can rewritten the poles S1, 2 means we have a 2 roots here, that is minus 1 plus or minus J4, where it is in the form of sigma plus j omega, right? So where sigma value is 0.1 and omega value is plus or minus 4. And again, sorry, the sigma value is minus 0.1 here. So now the omega value, how much we have? We have a 4 that must be mapped into the resonant frequency pi by 2. So we know that how to calculate an angle, that is we have a analog frequency and we also have a digital frequency. By using this you need to calculate what is total time here, that is t. So omega is nothing but 4 here, omega r is nothing but omega, that is pi by 2. So let's see what is the value we'll get for a t now. So t is nothing but 2 by omega tan of omega by 2. 2 by omega value is 4, tan of pi by 2 into 1 by 2 will get pi by 4. So finally the t value will get as a 1 by 2 second. Next what I need to do, we need to calculate what is the transfer function in frequency domain, right? So in frequency domain means you need to calculate what is h of z. So h of z can be calculated by using a bilinear transformation technique by replacing s by 2 by t into 1 minus z inverse divided by 1 plus z inverse. So that is, we know that what is HA of s, so that must be replaced by s, which is equal to 2 by t means the t value is 1 by 2. If I take it to the numerator it becomes 4, 1 into 1 minus z inverse divided by 1 plus z inverse. So the h of z is, if I substitute the value for a HA of s, that is s plus 1.1 divided by s plus 0.1 whole square plus 16, that must be replaced by s, which is equal to 4 into 1 minus z inverse divided by 1 plus z inverse. The next h of z is, now if I replace s by z, this term, that is 4 divided by 1 minus 4 into 1 minus z inverse divided by 1 plus z inverse plus 0.1 whole divided by 4 into 1 minus z inverse divided by 1 plus z inverse plus 0.1 whole square plus 16. So if I expand this term, this is in the form of a plus b whole square. We know the formula for a plus b whole square, right? That is a square plus b square into 2ab. So a square means this is a term, that is 16 1 minus z inverse whole square divided by 1 plus z inverse whole square. And b square means 0.1 whole square. For 2ab means 2, a is 4, b is 0.1 and remaining term is 1 minus z inverse divided by 1 plus z inverse. So plus 16. So in the numerator what we have taken a LCM as a 1 plus z inverse. If I take a LCM, if I simplify this one, you get this term. And finally try to take a LCM in the denominator also and try to simplify the term. And once we simplify the term, we'll get 0.128 z per z square plus 0.006 z minus 0.122 z square divided by z square plus 0.0006 z plus 0.975. This is a required transfer function for a digital filter by using given analog filter. Next, let's see how to solve the problems based on Butterworth filter. So in the Butterworth filter, this is a requirement they should give. That is, first they should give a transfer function. Transfer function must be ranges in if the omega value which is greater than or equal to 0, less than or equal to omega p means this is a pass band, right? So the pass band range must be a greater than or equal to AP, that is pass band attenuation, less than or equal to 1. So this is a range. And for the next one, if omega value which is greater than or equal to omega s means this is a stop band. So the amplitude value for this, that is AS. Next, how to calculate a cutoff frequency for this? Cutoff frequency means omega c, which is equal to omega cp. Cp means this is a cutoff frequency which is calculated by using pass band attenuation, pass band attenuation, and this is a cutoff frequency by using stop band attenuation. So that if I want to find out the total cutoff frequency of a given filter means we need to consider average of those two, that is omega cp plus omega cs, which is divided by 2. So let's see what is omega cp then. So omega cp is nothing but omega p, that is a pass band frequency, that must be divided by 1 divided by ap square minus 1 whole power 1 by 2n, plus omega cs is nothing but 1 by as square minus 1 whole power 1 by 2n. Omega is divided by 1 by as square minus 1 whole power 1 by 2n. If I have this AP and AS value in dB, then it must be a 10 power 0.1 AP in dB minus 1 whole power 1 by 2n. It must be a 10 power 0.1 into AS in dB minus 1 whole power 1 by 2n. So by substituting those values, you can easily calculate what is the cutoff frequency here. Then the next, how to calculate the order of the filter. So the order of the filter can be calculated using this formula, that is n, which is equal to 1 by 2 log of 10 power 0.1 AS minus 1 divided by 10 power 0.1 AP minus 1. So these two values are in dB, so which is divided by log of omega s by omega p. So in the discussion in the last video, we had discussed about how to calculate a n for a Butterworth filter. Over that, I didn't use this 10 power 0.1 AS, 10 power 0.1 AP. In that case, we used only 1 divided by delta A square. Delta A square is nothing but AS square minus 1 divided by 1 divided by AP square minus 1. So that is a attenuation value. This is also a attenuation value, but it is in dB. Then let's see one example based on this. See here, we have taken a problems based on Butterworth filter. The first example I have taken, they are given a characteristic equation, transfer function, in order to find out system function, that is HA of S, analog filter system function HA of S. Here they are given frequency value, transfer function, that is 1 divided by 1 plus 64 omega s. What we need to do, we need to we need to find out what is HA of S here. So HA of S means we know that what is the standard formula for transfer function for a Butterworth filter, right? So HA of j omega magnitude square, which is equal to 1 divided by 1 plus omega by c, omega by omega c whole power 2n. So what we need to do, we need to compare this expression with the given equation. So this given equation must be rewritten in this form. So that is omega divided by 1 by 2 whole power 6. So 6 can be rewritten as 2 into 3, right? So where we have a 2 as it is here, and 3 means that is a n value. And what about omega? In the numerator we have omega here also we have a omega. In the denominator what we have a omega c. What is the value of omega c now? That is 1 by 2 radians per second. So if I want to design what is the transfer function of analog filter, first we need to find out what are the poles of a Butterworth filter. So in order to find out the poles of a Butterworth filter, we have an expression, that is sk, which is equal to plus or minus omega c e power j n plus 2k plus 1 into pi divided by 2n. In the discussion what we have taken, over there I have taken it as a 2k minus 1 into pi divided by 2n, but k value which is started from 1 to n, but here we have started a k value from 0 to n minus 1, that's why we added a n here. So by using this, you need to calculate what are all the poles for a Butterworth filter. Because the order of our filter here 3, so 3 means there must be a 3 poles must be present here. So in order to find out a 3 poles means k value which is varies from 0 to n minus 1 means 3 minus 1 will get 2. So take a k value as a 0, 0 is not, which is equal to k omega c is 1 by 2 e power 3 plus e power j into 3 plus 1 into pi divided by 6. So we'll get 2 pi by 3. The value will get plus or minus 0.25 plus or minus j 0.433, and again take k value is a 1 and we'll get 1 by 2 e power j pi. The value will be minus 0.5 plus 0.5 and k value is a 2 because we have a plus or minus here, that's why we are getting a 2 poles here. Then S2 is 1 by 2 e power j 4 pi by 3. We'll get a value as a plus or minus 0.25 plus or minus j 0.433. So let's see how to represent these poles on a circle now. So see here, 3 poles will be comes in the left half of the S-plane and remaining 3 poles will be comes in the right of the S-plane on the circle with a radius of 1 by 2 radians per second. So see here, this is a radius with a radius value is 1 by 2 here. Next, always we try to consider the poles which are present in a left half of this plane in order to form a transfer function. We always try to neglect these poles which are present in a right half of this plane. So HA of S is nothing but omega c whole power n and divided by S minus S1 into S minus S2 into S minus S3. It will continue till the nth term. So here we have omega c value is 1 by 2 where n value is a 3, 1 by 2 whole power 3 whole divided by S plus S1 value is 0.5 and S2 value is 0.25 minus j 0.433 and S3 value is S2 value is S plus 0.25 plus j 0.433. If I simplify this one, we'll get the final answer as a 0.125 divided by S plus 0.5 into S square plus 0.5 S plus 0.25. So this is a required transfer function, analog filter transfer function. Then let's see the next example of a butterworth filter. If they are asked to design an analog filter with maximally flat response in the pass band and an acceptable attenuation of a minus 2 dB at 20 radians per second, the attenuation in the stop band should be more than 10 dB beyond 30 radians per second. Means they are given a data, you need to design an analog filter here. So what are the data they are given? Acceptable attenuation means this is passband attenuation. This is, so the passband attenuation is 2 dB. Don't get confused, they are given a minus 2 dB here means which is below to the 0. Below to the 0 means it must be a negative only, but while considering it as, we consider it as a plus 2 dB. Passband edge frequency we have, that is 20 radians per second. At 20 radians per second they are given. So the passband frequency is 20 radians per second. Then attenuation in a stop band, how much they are given? They are given a 10 dB and beyond means after omega p we have 30 radians per second. So this is omega s. So by using this, if you want to design analog filter means first you need to find out what is capital N here. So capital N can be calculated by using this formula. We know that is 1 by 2 log of 10 power 0.1 as minus 1 divided by 10 power 0.1 ap minus 1 log of omega s by omega p. See here, so they are given a AP and AS value in dB. So you can easily substitute the values here and you can easily find out what is N here. After substituting the values of omega p and omega s, what is the value we are getting for N is, that is 3.37. So always we'll try to consider the filter as an integer, means we'll try to round off the value of N to the higher value, that is N value is 4 now. So we are getting a 3.37, so we need to make it as a 4. So now the order of the filter is 4. Next, they won't given a cutoff frequency, so we need to calculate what is the cutoff frequency because they are given what is omega p and what is omega s here. And see here, they are given AP and AS value in dB, so it must be in the form of omega p divided by 10 power 0.1 AP in dB minus 1 whole power 1 by 2n, omega s divided by 10 power 0.1 AS in dB minus 1 whole power 1 by 2n. So substitute the values of omega p, AP, AS, omega s. So you will get omega c after simplifying this expression by using your calculator. So you will get omega c value as 22 radians per second. Next, after finding out omega c and n, the next step is you need to find out what are the poles we have. So poles, in order to find out p, k, s, k, take any variable you you can choose any variable, whichever the variable you are comfortable to represent a poles here. So that is plus or minus omega c e power j n plus 2k plus 1 into pi divided by 2n. Right? So substitute a k value which is ranges from 0, 1, 2, 3 because n value is 4 here. So p naught is plus or minus 22 e power j 5 pi by 8. So if I simplify this one, you'll get minus 8.419 plus j to 20.325, and another one plus 8.49 minus j 20.325. Similarly, p1 value will get as a 20 minus or plus 20.325 plus or minus j 8.419, and p2 value is minus or plus 20.325 plus or minus j 8.419, and p3 value is minus or plus 8.419 plus or minus 20.325j. So these are all the poles, and along with that we need to choose this one, which are all the poles which is comes under left top of the S plane. Then those poles we need to use in order to form a transfer function. So that is, we have minus 8.419 plus j 20.325. So minus complex conjugate poles we have, right? So those poles we have which comes under left of the S plane, substitute here in this expression. So after simplification of that, so you'll get s 22 whole power 4, that is omega c power n value, that is s square plus 16 into 8 power 3 8s plus 484 into s square plus 40.65s plus 484. So after simplification, after substituting what is s1, s1 star, s2, s2 star, so after substituting, after multiplying these two, we'll get this expression. So this is a final required transfer function for a butterworth filter. Then next, this is an example for Chebyshev filter. So they given design an analog Chebyshev filter with the following specification. They given a passband ripple as a 1 dB for 0 which is less than omega value which is greater than or equal to 0, less than or equal to 10 radians per second. Stop band attenuation is minus 60 dB for omega value which is greater than or equal to 50 radians per second. And in case of your omega p value is nothing but omega c. There is no cutoff frequency here. Cutoff frequency is exactly at passband frequency. So let's see how to design a Chebyshev filter by using the following specification. So first what we need to do, we need to identify which are all the specification they are given. They are given AS value is 60 dB, AP value is 1 dB, omega p is 10 radians per second, omega s is 50 radians per second. Again, to find the order of the filter, so we have an expression for a Chebyshev filter as a cos hyperbolic inverse square root of 10 power 0.1 as in dB minus 1 divided by 10 power 0.1 ap in dB minus 1, which is divided by cos hyperbolic inverse of omega s by omega p. Substitute the values of ap and as here, and omega p and omega s. Try to calculate n value. We'll get n value as a 3.61. So we need to choose it as a n value as a 4. If order is a 4, then n is even now. So if I have a n value as a even, we have a standard equation in order to find out HA of S, that is omega p power n continued product summation k which is equal to 1 to n by 2 into ck, that should be multiplied by 1 divided by root of 1 plus epsilon square whole divided by continued product equation, that is k which is equal to 1 to n by 2, that is multiplied by s square plus s square plus bk into omega p into s plus ck into omega p square. So here the n value is 2, right? So n value is 2 means we have our unknowns here. One is ck, another one is bk. We do another one is epsilon here. So how to calculate a bk? To calculate a bk, we have an equation, that is 2yn into sine of 2k minus 1 into pi divided by 2n. And again ck can be calculated yn square plus cos square of 2k minus 1 into pi divided by 2n. So yn can be calculated by using this formula, that is 1 by 2 of square root of 1 plus 1 divided by epsilon square plus 1 by epsilon whole power 1 by n minus root of 1 plus epsilon 1 plus 1 divided by epsilon square plus 1 by epsilon whole power minus 1 by n. So first we need to calculate what is epsilon here. Epsilon can be calculated by using square root of 10 power 0.1 ap in dB minus 1. So if I substitute a value of ap here, we will get 0.508 as epsilon value. Substitute epsilon value in this expression. In this expression, we'll get yn value as a 0.3647. So once we get a yn value, substitute here bk. K value is varies from 1 to 2. So b1 is 2 into yn value is 0.3647. Sine of k value is 1 here. So we'll get pi by 8. We'll get answer as 0.27912. And again take k value as a 2. b2 is 2 into 0.3647. Sine of 3 pi by 8. We'll get answer as 0.3 0.67387. Next you need to find out what is C1 and C2 here. C1 is yn square means 0.3647 whole square plus cos square pi by 8. So it is in the form of cos square theta. It can be taken as cos 2 theta plus 1 divided by 2, right? Because we can't find out what is cos square theta value directly. So for that you need to use a trigonometric formula. Next, substitute the values. We'll get a C1 value as 0.9865 and C2 as 0.27947. Substitute all those values in a transfer function. We'll get as this function, that is 0.9865 into 0.2794. This is C1 value, this is C2 value, this is this term, and which is divided by s square plus 0.27912s plus 0.9865 into s square plus 0.67387s plus 0.2797. The final transfer function after simplifying this one will get 0.24573, which is divided by s power 4 plus 0.952 s cube plus 1.45 s square plus 0.7426 plus 0.275. Here the omega p value we are considered as a 1 radians per second because we have considered a normalized filter here. Thank you.